Welcome to The Explainer. Today, we're diving deep into the revolutionary architecture that powers pretty much all the AI you hear about, from ChatGPT on down, the Transformer. This is the engine that truly changed the game for AI and language. All right, so here's our game plan. We're going to start with the basic mission. How do you even teach a computer to understand language? Then, we'll get into the nitty-gritty of turning words into numbers. After that, we'll look at a huge problem that stumped researchers for years, the problem with memory. And that's going to lead us right to the big breakthrough, the idea of attention, and how it all gets put together inside the transformer. So first things first, what are we even trying to do here? Well, the whole goal of NLP, or natural language processing, is to give computers the ability to understand, interpret, and, even generate human language. It's really all about building a bridge between our world of words and their world of ones and zeros. Now, this big mission breaks down into a few key jobs. Sometimes you just need a model to classify something, like, is this movie review positive or negative? Simple enough. Other times you need it to find specific things, like all the names and locations in a news article. And then, of course, there's the one we're all fascinated by right now, generation. That's where you ask the AI to create something totally new, like translating a sentence or summarizing a huge document. But right away, we hit a fundamental wall. You see, computers don't speak English or any human language. They speak math. So the first giant hurdle we have to clear is figuring out, how do we translate our words into numbers that a machine can actually work with? The very first step in this process is something called tokenization. You basically have to slice and dice a sentence into smaller, bite-sized chunks called tokens. Seriously, think of it like chopping up vegetables before you start cooking. You're just getting all your raw ingredients into a form that the system can actually handle. But, how you do that chopping actually matters a lot. A simple way is to just treat every single word as its own token. But the problem is, the model would see run and runs as two completely different, unrelated things. A much smarter way, and this was a real light bulb moment, is to use subwords. A subword model is clever enough to see that runs is just the root word run, plus an S. This makes it way more flexible and way better at dealing with words it's never seen before. Okay, so once you have your tokens, how do you turn them into numbers? Well, an early attempt was this thing called one-hot encoding. You'd basically create this massive list of all possible words, and for each word, it was all zeros except for a single one in its own unique spot. But this had a huge flaw. Mathematically, it meant every single word had zero relationship to any other word. The model had no clue that teddy bear and soft are concepts that should be really close together. The real breakthrough was when we started learning these numerical representations. We call them embeddings, by just having the model analyze massive amounts of text. So instead of just marking a word's position, these embeddings actually place words into a sort of map of meaning. And this is what allows for that mind-blowing vector math you see right here. You can literally take the vector for king, subtract the vector for man, add the vector for woman, and the result is incredibly close to the vector for queen. It's math that actually gets relationships. All right, so we can represent individual words. That's a huge step. But it's only half the battle, right? Because a word's meaning totally depends on the words around it. And this brings us to a really fundamental problem in AI, the problem of context and memory. Early models, like what we call recurrent neural networks, or RNNs, they try to solve this the way a human would, by reading a sentence one word at a time. So they process the first word, create a little summary of what they've seen, and then pass that summary along to the next word, and update it, and pass it to the next, and so on. And, for short sentences, that worked okay. But what happens when you're not dealing with a simple sentence, but a long, complex paragraph? The model's memory just starts to break down. The important context from the beginning just gets lost in the noise by the end. And this points to the core technical issue, which has a name, the vanishing gradient problem. That signal, the important meaning from the first few words, just gets weaker and weaker and weaker with every single step. It's like a fading echo. By the time the model gets to the end of the paragraph, it has literally forgotten how it started. This memory problem was a massive roadblock for AI. To get past it, we needed something totally different, a completely new way of thinking. And this brings us to the breakthrough that changed absolutely everything. So in 2017, a paper comes out with this incredibly bold, almost arrogant title that says it all. The authors basically said, forget trying to cram everything into some sequential fading memory. They proposed a radical new mechanism called attention. The idea behind attention is just, it's so elegant and powerful. It completely throws out that one-by-one sequential process. Instead, it allows every single word to create a direct data connection to every other word in the sentence, all at the exact same time. All of a sudden, it doesn't matter if two related words are right next to each other or 100 words apart. Distance is irrelevant. So how does this work? Well, it relies on three concepts that the model learns: a query, a key, and a value. Let's start with the query. Think of each word as sending out a little signal, basically asking a question. Hey, to understand what I mean right here, who else in this sentence should I be paying attention to? Now, to answer that question, every other word has what's called a key. A key is kind of like a label or a signpost on that word that advertises its role and its meaning. It's the word's way of saying, hey, over here, this is the kind of info I've got. And finally, if a query and a key match up, there's the value. The value is the actual substance of that word, its real contextual meaning that can then be shared across that connection. So here's how it all clicks together. For any single word, its query scans all the keys across the entire sentence, looking for good matches. When it finds keys that are relevant, it pulls in a weighted mix of their corresponding values. And the result? The word's original meaning gets instantly updated and enriched with context from the most important words around it, no matter how far away they are. It's brilliant. Okay, so we have this incredibly powerful new tool, this attention mechanism. So how is it actually used? Well, it's the core engine inside this elegant architecture that we now call the transformer. If you zoom way out, the architecture has two main parts. First, you've got the encoder. Its entire job is to read the input text, say a sentence you want to translate, and build a really deep, rich, contextual understanding of it. Then you have the decoder, which takes that rich understanding and uses it to generate the output, like the translated sentence. Let's just walk through how this works for a translation. So first, the encoder takes in the entire input sentence all at once. It uses that self-attention magic to build a really good map of what everything means. Then the decoder kicks in. It starts with a simple question. Okay, what's the first word of my translation? To figure that out, it attends back to the encoder's map, finds the most relevant info, and predicts the first word. Then, and this is the cool part, it adds that new word to its own memory and repeats the whole process for the second word, attending now to both the original sentence and the word it just wrote. It just keeps doing this step by step, word by word, until the job is done. So to pull it all together, let's recap the secret sauce. You've got self-attention at the very core, which lets words figure out their context. Then you have multi-head attention, which is like running a bunch of attention scanners in parallel, where each one is looking for a different kind of relationship. You have to add positional encodings back in just to remind the model of the original word order, and you wrap this all up in that powerful encoder-decoder structure. That's the whole shebang. You see, by solving that deep, long-standing memory problem, transformers didn't just make things a little bit better, they unlocked an entirely new universe of possibilities for AI. It created a new level of coherence and understanding that we just hadn't seen before. And it leaves us with this final thought. What's the next great frontier? What becomes possible in a world where every piece of information can have instant, meaningful access to every other?